Hey there everyone. Now it's actually getting a little bit more exciting because we are learning about one of the most important machines in measuring masses, which is known as the mass spectrometry machine, or mass spectroscopy, the operation is. So you may have wondered, how do we measure the mass of a very small particle like an oxygen ion, or an iron ion, or a copper ion, or something like that? These are very small, or alpha particle, or all of these charged particles. It has to be charged to be able to measure it. How do we go about doing that? Well, it has to do something with the velocity of the charge itself that we can bring it up to, then the magnetic field, and tuning the velocity with the magnetic field, then measuring the radius, and then from there we can take it and play with some equations and find the mass of that ion. Let's see how that goes. Okay, so let's say there's a schematic diagram of the mass spectrometry machine. Let's say there is a source of ion here, like hydrogen ions, like H1 plus, or Fe plus 2, or copper plus 1 or plus 2, and these are being spit out by this ion source. They come here and they sit here, okay, at a velocity that is equal to 0, but we expose them to a potential difference and we accelerate them and compress it in a beam like this. Like maybe we can use some sort of like electrical and electronic instruments to compress the beam, okay, and we accelerate it through a potential difference, and as soon as, let's say, the charge here, so the charge is going up, let's say it's a Q0 positive charge, and let's use the right hand rule. As soon as it gets into the vicinity of the magnetic field, it's going to change its trajectory. Let's see how that goes. So this is the magnetic fields going to the page. Okay, here we go. The direction of the magnetic field is going to the page, and the velocity is up. Look, so that's the velocity. So then the force will be the palm of my hand pushing it this way. Okay, good. So the charge will start making what? A circular path. And as soon as it forms this path, it falls into a screen, and it makes a bright spot here on the screen. An operator will come and measure that bright spot. Knowing where it started, they can actually do what? This is the radius, this is the radius. They will know what the radius of the circular trajectory. That is one of the piece of information we will need. We will need other things. So radius is known. So known quantities. Radius. The magnetic field, of course, we know what the magnetic field is because we create the magnetic field. We know what the value of it is. We also know what the voltage, so that's V, the voltage at which these charges were accelerated. And that's it. That's good. That's good enough to know. So we know the radius, the magnetic field, and the voltage. All right. Now let's look at the equations we learned so far. We knew so far that the radius is equal to the mass times the velocity divided by the charge Q times B. Okay. We also learned if a charge is accelerated from rest and it goes through a potential difference, because of it's accelerated from rest through a potential difference, the Q times the potential difference itself is equal to 1/2 times the velocity, 1/2 times the mass times the velocity squared. That's good. Now we can write this equation, we can put these equations together. We're going to end up with an equation that combines these two together and gives us the mass of the ion that we're looking for. So how do we do that? Okay, let's write this equation here in terms of V squared. So V squared is equal to Q times the voltage, now times 2 divided by the mass. Okay, now we have in this equation also v squared, v. So let's write this down equation here so that we want to get rid of the velocity. R square is equal to the mass square, because I'm squaring this whole equation, times velocity square divided by q square times b square. Now take this v and put it here, v squared. Okay, so this becomes like this: mass square, now v squared is equal to 2q, okay, times the potential divided by the mass. I'm going to put it on the top, and this whole thing is divided by q square times b square. Now q square, the square goes with q, and this mass goes with the square of the mass, so we end up with this equation: r square is equal to the mass times 2 and times the voltage difference divided by q times b square. Okay, now I'm going to rewrite this equation in terms of the mass, because we're looking for the mass, and thus the mass spectroscopy. Mass is equal to q b square times r square divided by 2 times the voltage. Now let's check what we know, what we don't know. We need to know the mass. Okay, do we have the charge? Yes, because when you make an ion, basically you know if it was +1 or +2 or -3 or whatever. Okay, and of course +1 means it has lost an electron, so if the charge on it is 1.6 times 10 to -19. If it's +2, it means it lost 2 electrons, so the charge on it is 1.6 times 2 times 10 to -19, and so forth. And the radius is known from this kind of like the spectrometer gives it to us. The voltage is known because we make it. The magnetic field is known because we tune it, and so forth. So this is a good equation for the mass spectrometry. Okay, it's very good equation to remember and to know. And then we can have some examples now. Thank you.